Hey everyone, my name is Taylor Sparks and I'm the editor-in-chief of Integrating Materials and Manufacturing Innovation. Now our journal has to do with materials and manufacturing, it's right there in the title. And part of that means that you are going to have workers who might be exposed to hazardous conditions. And an important part of that, obviously the first line of defense is proper training and knowledge so that you avoid problems in the first place. But the second is going to be your personal protection equipment. And PPE compliance is a big deal in industry, particularly in the steel production industry. Today's paper deals with that exact topic. It is a dual model approach to industrial safety. They're going to have two different things. One is going to be a computer vision model for detecting PPE compliance, and a second will be hazard zone monitoring. And they're going to do this in the context of a steel production plant. This comes to us from the folks at the Center of Innovation through Visualization Simulation at Purdue University Northwest, and from Steel Dynamics Incorporated, lead author Kyle Toth. Okay, so in the steel fabrication industry, there's a variety of different PPE that is required. For example, you have eye protection, head protection, hand protection, body protection. But mistakes happen. People will accidentally forget to put goggles on. And what would be great is you had a real-time feedback that could alert the individual that they've forgotten a piece of PPE to get better compliance and prevent potential injury or harm. The authors in the introduction talk a little bit about the fact that there are already sort of PPE models that can detect PPE, but the challenge is that you really have two tasks. You need to detect the person and the PPE, and if you try and rely on one model to do both of these things, they don't do a very good job. So one of the innovations that they've done in this paper is they've intentionally split that up. So a user can be monitoring via, say, a video or image feed from a camera. You pre-process this data, and you're going to separate out two different models, one that is going to do human detection, and a separate one that's going to ask whether or not PPE is detected. And then you're going to merge these together to actually perform the PPE compliance checking. Now, the second thing that they do, and that alone would be great, but this is clever. They also have this marking up of their no-go zones in the factory. So they have labeled regions of the factory as hazardous zones, right? So these zone checks can also be done. You can detect whether people are in those zones because you've already done the human being detection, and now you can overlay that to see whether there are individuals in those zones. And then you take the output of these different checks, the zone check and the PPE check, to have an alert or a log, and then you save the video and as a result to go into your compliance files. And here's just an example. Again, camera would observe individuals, and then you would have your tool that they've built here to do bounding boxes for the humans in red, bounding boxes for the PPE, identifying them, those are the blue boxes. And then you would also check against compliance, whether we have the right PPE equipped or not. The performance of this original model that didn't include the hazardous zones alone was pretty good. They were getting over 90% in their F1 score for both worker detection and for PPE detection. Here's an example of it detecting individuals shown in the red bounding box, but now it's within a region of the image that has been labeled as a hazardous zone. The performance on the model of detecting individuals in these hazardous zones was similarly above 90% for the F1 score. And something that's, I think, pretty slick about this in terms of actual implementation, if you wanted to use this tool, is this ran on a standard GPU, and this was able to have essentially real-time feedback for an actual system that could catch mistakes as they're being made. For example, they showed that they were able to get the scores that they've presented here, even while maintaining a 35 milliseconds per frame refresh rate on the video. And then last of all, they have some really helpful sort of discussion about the limitations and future work about where this could go in the future. Clearly, this is an impressive tool, even as it is, but it does have some limitations that I think it's wise that they point out. First off, there's definitely some sensitivity to the environment, specifically visual quality, right? So they talk about the reliability detection under low light scenarios or high glare from reflective machines, especially for things like goggles and gloves. It said glove identification dropped to less than 20% in the instance of low light frames because of motion blur and inadequate contrast. The other one is the absence of historical background, right? So these are individual frames that are analyzed apart from the time series of data that they were collected in, right? That could potentially be a future work that you could extend this to have the sequential data capturing the temporal nature of this, but currently that's not captured. And that may be relevant because it says during occlusion, when something gets hidden behind a machine or something, this can lead to conflicting predictions, and sometimes that might generate false alarms, and that might erode operator confidence. You may not trust the machine if you get enough false alarms. They talk about the problems here. One other one is that they're assuming the camera is staying fixed, right? That's how they were able to mark out the no-go zones, by pixel defining the regions in this fixed camera location. But in the real world, cameras don't always stay fixed. There could be vibration. Maybe the mount changes its location or gets partially blocked. And under those scenarios, the accuracy system wouldn't be guaranteed. In fact, it would probably require retraining. Another limitation is there are only 4 categories of PPE that were used here: safety vest, gloves, goggles, and helmet. But there are, of course, other ones that a plant might require, such as steel-toe boots, ear protection, or fire-resistant clothing, and that was not specifically included in this approach. The next one is that there's no worker tracking, right? It says there's no long-term identification done. Therefore, it's tricky to get, the statistics that you might be interested in by looking at practices over time or analyzing trends, because again, you're not tying it to specific individuals. And then the last hazard or caution they throw out there is like, hey, this is a small set, right, of data, and our model could be overfitting to plant-specific visual traits. Not actually finding the individuals, but something around the individuals that's causing it to look like it's performing correctly, but may not be, right? That said, I think that this is a pretty impressive paper, and kudos to the team and for making the parts of the data available that they were able to make this useful for other people that want to build on this work. And I hope that you'll read all about it in the latest issue of IMMI.